Good afternoon, everybody. This is Roger Frechette, and welcome to our Interface Engineering High Performance Buildings free webinar series. We are going to be getting going in just a minute or so. Going to give a couple minutes. I see a lot of people are dialing right now. This is the first of a series of educational webinars that will be provided by our organization over the next few months. And today's discussion is going to be a case study on the American Geophysical Union, AGU, net zero energy office building in Washington, D.C. And today's session is an accredited AIA course. We are a certified AIA provider. And if you look to the lower left-hand corner of your screen right now, our course number is M17-0682. So if you are in need of AIA learning units, please make note of that number and use that for your submission. If you filled out your course number on the registration page, we will be emailing you a certificate with the 1-hour learning unit. So with that, it seems like we have enough people online to get started, so I'm going to jump right into it. So the course description for today is we're going to be making a presentation on net zero energy design. This course was developed for architects, engineers, and leaders in the built environment. And it really is to focus on a methodology and an approach to renovating existing urban buildings and converting them into either net zero energy or positive energy buildings. The presentation is going to touch on a number of strategies that are used within our firm and with others across the country. And again, we're focusing on the AGU headquarters building in Washington, D.C. We will talk about system options and how they were bundled together. And we're going to highlight opportunities and challenges with design, permitting, construction, and commissioning of these projects. And then we're going to be talking about a number of the specific strategies used to get this particular project to and beyond the net zero energy threshold. Some of the challenges, some of the opportunities that we came across in that effort. So the learning objectives for this course: one is to gain an understanding of the definition of attributes of net zero energy. Second, to talk about a 4-step process that we have developed in coming up with an approach and bundling energy conservation measures to get to net zero. Third, to learn about the modeling that is required to be able to demonstrate that your building is net zero energy or better. And then lastly, to talk about some specific lessons learned from our experience on the American Geophysical Union headquarters. So 10 items that we're going to touch on as we go through this presentation. What is net zero? The mission of AGU, project constraints, the role of forensics, baseline modeling, net zero energy plan, the high performance measures, the energy results, how AGU is making an impact with the building. And then I'm going to leave some time at the end for questions and answers. In this GoToWebinar format, you should have the ability to post your questions, and at the end, I will scroll through and answer as many as I can with the time left. So starting out, what is net zero energy? This is an example of a net zero energy building, and as a matter of fact, for many thousands of years, all the buildings that we created were net zero, buildings that do not require electrification for their operation and use. It has only been really since the late 1800s with the advent of elevators, electric lights, and ultimately computer equipment that has required us to use electricity in buildings. In fact, some time ago, we were even good at designing and building what we call positive energy buildings. And these are buildings that have the capability of generating more power than they consume. But in terms of the modern use of the terms net zero energy and positive energy buildings, we are looking at buildings that, particularly on the site that they operate, have the capability of generating at least as much energy as they consume. There's an organization known as the New Buildings Institute that tracks all of what they call the emerging or under design construction phase of the projects and verified net zero energy buildings from across the country. As of this morning, there were 527 that were still in process and 121 buildings that have been verified as being net zero energy. 648 buildings might sound like a lot, but given the fact that we have many millions of buildings across the United States, and given that many jurisdictions are contemplating code changes to push towards net zero energy buildings, it is a very small fraction, but it is a good starting point. I put the slide together with a couple things I wanted to point out. One is that when you look at the buildings that have been successful in pursuing net zero energy, there's a lot of commonality to them. We find that there's a lot of residential buildings in the mix, and we find there's a lot of educational buildings in the mix, predominantly K through 12 projects. And just looking at the image in the lower left-hand side, this is what we find in many places across the country. Single-story buildings with big flat roofs and the opportunity to put a lot of photovoltaic or solar technology on the roof. The ratio in these buildings is 1-to-1, one area of roof versus one area of conditioned floor space. And you'll see that even with this 1-to-1 ratio, it can often take a large cross-sectional area or a large area of photovoltaic panel to be able to achieve that net zero condition. So you can imagine as the building gets built taller, if this building were 2 buildings, you would have the same roof area, but you would have twice as much conditioned area. Hence the problem with trying to get taller buildings to net zero. In fact, when we looked at the 648 buildings, most of these buildings are 1- and 2-story buildings. So the challenge is to be able to make a real impact on the energy profile and carbon emissions associated with buildings in this country. We need to find a way to get office buildings to net zero energy. And again, the taller the building gets, the more difficult that becomes. So our firm gets involved in a lot of net zero energy designs, and I put a couple examples up here. And in both cases here on the left, a headquarters building for the IFC in Dakar, Senegal, and on the right, a confidential pharmaceutical headquarters building. These are both new buildings, and you have the advantage of being able to think about materials beforehand, to think about solar orientation, to make best advantage of the landscape as a potential energy source. So I would argue it is a lot easier to demonstrate net zero energy in a new building versus an existing building. With existing buildings, you need to work with what you have. Now, the reality of it is, if we look as a country to make a big change and move towards net zero energy, we are not going to be knocking down all our existing buildings and building new. We will need to find a way to reposition a large portion of the country's existing building stock and renovate it to a net zero energy or positive energy condition. Which really leads to this particular case study. In my mind, it is the key to have the ability to look at our existing office building stock in major urban areas and find a way to economically convert them into high performance, low energy, net zero energy, positive energy buildings. That is what will move the needle. So that brings us to AGU, the American Geophysical Union headquarters. AGU is an organization of about 60,000 Earth and space scientists. It's an international organization. It celebrated its 100-year anniversary just last year, and in serving these Earth and space scientists, it was looking for ways to be able to reflect the mission of the organization. And of course, with all these scientists, there's many of them, most of them, believe that carbon is a great threat to our world, and that building design, construction, and operation is one of the major contributors to the carbon problem. But this is an image of the existing headquarters, or I should say the before the renovated condition of the AGU building. And it was originally built in the late or mid 1990s, and had over the years it was maintained in pretty good condition, but the mechanical systems in the building began to reach the end of their useful life, and the organization decided it was time to replace those that MEP or mechanical equipment. Now, rather than just replace in kind, the organization decided to explore what would be possible, and began to ask the question, is it possible to renovate a building like this and approach net zero energy or net zero water within the design and construction? And our organization, along with an architectural firm by the name of Hickok Cole, a program management firm by the name of MGAC, were brought together to explore those possibilities. So the AGU building has been at this location for many years. Before the pre-renovated building, there was another headquarters building that had been knocked down, but AGU has resided in this neighborhood for a long time and has become a strong part of the DuPont Circle neighborhood in Washington, D.C. When I would tell people that we were involved in the project, one of the first things people would always say to me is, "Oh, the building with the planets and the sidewalk." So there are planets in a solar system that stretches across the sidewalk, and it's amazing how simple elements like this can really connect the building and the organization to the community and to the local residents. The building location, it sits along Florida Avenue and 20th Street in Northwest Washington, D.C. It is about a half a block off of Connecticut Avenue. So some of the project constraints, the number one constraint I would say is that it is an existing building, and we did not have the opportunity to start from scratch with all the materials and solar orientation and all that might be most appropriate for that site. And you will also notice that the building is built right up to the road on two sides. There's an alleyway on the third, and the building is built right up to and abuts an adjacent building on the back. So there is no surrounding land area to consider things like, geothermal systems or on-site solar. That is not roof mounted, so that was a limitation and a constraint. But this diagram shows perhaps what was the largest constraint of the building is that the project site sits within what is called the DuPont Circle Historic Preservation District. It is literally just inside it. If we were on the other side of the road, we wouldn't be there. But being in a historic district, there's a lot of concern whether or not anything that we would want to do to the building on the exterior would really be allowed. There's a lot of scrutiny that takes place in seeking these approvals. And to be able to get to net zero, well, we would need to apply technology to the outside of the building. So not only would these changes require relief from zoning, we'd have to go through BZA, the Bureau of Zoning assessment. I forget the acronym, I'm sorry, but we needed to get relief from the BZA. We also needed to get approvals from the Historic Preservation Review Board. So this is a term that I've known about a long time, NIMBY, acronym that stands for Not in My Backyard. And quite often when you're looking at doing something new or different or potentially considered odd looking within a neighborhood, a lot of people come out and state their dissatisfaction with the plan and show their opposition to such development. But I learned a new term along through this project, and that is a YIMBY, also an acronym, Yes in My Backyard. And this became very important to the success of the project. And that's the back of my head there on the right-hand side. But when we showed up at the Historic Preservation Review Board, I was quite amazed with the number of individuals that showed up from the neighborhood and from various neighborhood organizations that asked to address the panel and explain to them how important this project was and how much they hoped that the board would consider this project moving forward. Because they thought it was so important that Washington, D.C. become a leader in high-performing building design, and that our new buildings become very sustainable and responsive to the growing problems that we have with carbon emissions in the country. So before we could jump into design, and because it was an existing building, we really needed to take a close look at what we had to start with and understand the characteristics of all of the elements and materials that we anticipated bringing forward. And we took these at the very, very beginning of the project. This was some thermal imaging. And when we looked at the envelope of the building, there was some things we expected and some things that were a surprise. One thing that we expected, you can see in these images on the left-hand side, these windows that are purple, meaning that there's more energy passing through the windows than the walls. That's not unusual at all, and we expected that. But then we saw this purple band that you can see on the left side. I'm not sure if you can see my cursor, but it was also glowing purple. And that we didn't understand. This element is a precast relief that wraps the buildings, quite an interesting element that has stars and planets embedded into it and representative of AGU. But we didn't understand why so much energy was leaking through that one element. And then we went back and looked at the previous construction documents from years ago and realized that insulation was never put behind this element. It wasn't a miss in construction. It was a miss in the design. It was not shown in the detail. So we did a quick calculation just to demonstrate to AGU how much energy and how many dollars have been spent in offsetting that energy loss each year and through the life of the building, and it was a substantial amount of money. So detail matters. So to be able to show the impact of all the different strategies we were considering, we needed to develop a baseline. And we developed a baseline energy model. This diagram was to show that relief that I was just talking about. But within this baseline energy model, we created a digital model using a industry accepted energy modeling software. And we created a model to show how much energy the building would predictably use through the course of the year. Now, when you build one of these models for a new building, you just take it at face value that is your baseline. In this case, we had an existing operating occupied building, so we could compare the results from this building to actual energy utility bill data. So when we looked at the data, this graph on the top, it shows the kilowatt hours that are consumed through the course of a year. And then on the bottom, how much natural gas had been consumed through the course of the year. But then there was a process we needed to go through where we had to reconcile the performance of this digital model we created to the actual building. And it was a painstaking process. And I would say this is a result overlaying the digital model to the actual building results. We were not able to get them exact. We got them very, very close, but we got them within a close enough standard deviation so that we could call our digital model a suitable baseline to then test all the all the energy conservation strategies on our list. So now that we understood the building, the existing building, and now that we've modeled the existing building, now it was time to come up with a strategy of how we were going to take this building, which wasn't terrible. It used a lot of energy, but it wasn't terrible, but how to get it from that condition to net zero energy. And we established this four-step process. Four-step process: reduction, reclamation, absorption, and generation. So reduction is essentially a list of strategies that all have one goal and purpose, and that is to reduce the building's appetite for consumption. They all reduce the amount of kilowatt hours per square foot per year that the building needs to be able to function properly. So we had a large list of reduction strategies. Then we created a list of reclamation strategies. Reclamation strategies are all strategies that look to take energy that is already inside the building and to capture it, not let it out of the building, and reuse it over and over again. Thirdly, we looked at absorption strategies, and these are a little bit different. This is really looking at forms of energy that move around the building or under the building or near the building, and look for opportunities to draw that energy into the building for the building's benefit. And then after you've done those three strategies, now you've reduced the building's what they call EUI, energy use intensity, measured in kilobTUs per square foot per year, but you've got the smallest energy footprint that you can get. And then and only then do we look at the generation piece, the strategies such as solar PV to generate the power to offset that smaller footprint that you've been able to achieve. So because AGU is a scientific organization, we were very precise with how we went about analyzing all the different energy conservation measures and coming up with a methodology for being able to select the right ones for the building. There were nearly 100 strategies that were put forward as part of a charrette that we had with all the project stakeholders. From that list of 100, AGU did tell us that they did not want to be guinea pigs, meaning they did not want to be the first building in the world to try something out that had never been done before. They just didn't or weren't prepared to take on that risk. So that reduced all the ideas that we had from 100 down to about 50. And for each of the 50, we wrote a white paper. And within the white paper, we looked at everything from the amount of energy that could be saved, to first cost, to operation and maintenance issues, to we had a number of different characteristics that we looked at, and each paper was structured the same way so that we could go through and properly compare and contrast the benefits for each of the strategies, because we certainly did not need all 50 to be able to achieve net zero energy. So of those 50, we made our selection. We created what we called our bundle of 23. And on the right-hand side of your screen is the list of the 23 strategies that were used to attempt to get to net zero energy and to get to net zero water. And if we had 3 hours today, I would go through all of them, but we don't. So I've hand selected about a half a dozen of them to take you through. So once we had our strategies dialing ahead, we spent about a year or so developing our detailed design documents, our permit documents, our bid documents. So the job went out to bid, was awarded, and it was time to get going on the implementation of the design. Much of the interior of the building was completely stripped out down to bare concrete. And even the windows on the building had to go to be able to achieve what we needed to achieve. The exterior walls were peeled back all the way to the exterior brick, and the roof was more or less scraped clean. And that gave us the starting point that we needed to be able to start to introduce some of these technologies. So the high performance measures, and again, can't go through all 23, but I'll touch on a couple. First thing we need to do, those windows that we took out needed to be replaced. So the windows were replaced with a very high-performing triple pane glass. We studied 16 different glass types, not only from a performance standpoint, but from a first cost standpoint and a life cycle cost standpoint, and ultimately picked one glass that was optimal for the conditions that we were trying to achieve. And then we needed to shade the glass. Initial thoughts were that we would do operable blinds on the inside of the building, but then we began to look at what is called dynamic glazing or electrochromatic glazing, where the glass itself has the ability to shade to reduce the amount of solar heat gain that passes through the glass. And one really nice thing about this technology is it can be linked directly to the building's energy management system. So we can be looking at outside solar conditions, internal daylight conditions, and adjust the tinting of the glass to optimize the energy performance of the facade. And the building also has overrides. So if, for example, you had a conference room that you wanted some privacy, you could override the system and darken the glass in that one particular room. In fact, every single pane of glass in the entire building can be operated separately than every other pane of glass. But the notion is that on a cloudy day, the glass in the building is quite clear. When the sun comes out, there's more daylight coming into the building, and the building has lighting sensors on the outside of the building, and the building responds automatically to that increased light level passing through the envelope. This is an image of the fifth floor of the AGU building, where you can see not only can you darken a single portion of glass, but there are layers of film on that glass where on one piece of glass you can shade the top piece of the glass and not the rest of it. So tremendous amount of flexibility in terms of how the shading occurs on the envelope. The next system, which I believe is the first in the country, is an easy word to pronounce. It's called hydroponic phytoremediation. And it's hard to repeat 10 times, but we gave it an acronym. We called it a HY-PHY wall. And essentially what it is, it's a green wall, and we've seen green walls installed in many places around the country, but this one is a little bit unique. Here's an image of what it looks like. Essentially, it's a hydroponic system where the plants sit within trays of water. There's no dirt in the system, and air passes through the leaves and then is forced through the trays of water, through the roots, and back through on the other side. This process helps clean the air. It removes a lot of VOCs in the air. It has the ability to do some oxygenation of the air, but it functions as a natural filter. And the reason that our system is different than what you typically see is our system is actually integrated into the building's HVAC system. And in lieu of having filters that filter the air on their way back to the HVAC system, we use this wall system to handle that level of filtration. Beyond the energy benefits that we get from this type of a wall, we also have the ability to, it's a beautiful element that's inside the building. So it's in the corridor areas of the building on every floor. So as people walk by it, they get to see the green wall. So there's a biophilia aspect to having the green wall there. And in addition to that, these green plants are constantly irrigated. And as they're irrigated, the water flows through them. It sounds like a small waterfall. So you have an acoustic and a visual element that add to the health and well-being of the occupants, in addition to the energy-saving attributes of the system. But essentially what happens is, most office building mechanical systems deliver air to the building, and that air then needs to be collected and brought back up to the air handling equipment, whether it be in a room or on the roof. And this does the same, but the air is forced through the green plants first. The air then rises up. And what happens here is the air quality is better in the shaft than it is in the space. By the time it gets to the top of the building, we have 16 different measurement devices within the airstream where we look at an array of different contaminants. If it demonstrates that the air quality coming back through the building is better than the outside air, it'll use the recirculated air from the building instead. And given this building sits right on Florida Avenue, and during the morning and the afternoon, it can be gridlocked with traffic. We expect that the building will have better air quality by recirculating than it will by taking outside air and for a fair amount of the time. Because the outside air in Washington, D.C. is very hot and humid, it takes a tremendous amount of energy to dehumidify and cool that air. So if we can, with a system like this, we don't have to use all that energy for all that outside air, and the occupants end up with a better quality airstream and better health attributes as a result of it. So this is the installation at on one of the floors within AGU's building. Now I mentioned that these green walls need irrigation water, and we're trying to get to. We had a goal to get to net zero water, so we needed a water source for them. But not only water for the green walls, we needed water for toilet flushing. We needed water to wash off our PV array on the roof. We do have some irrigation requirement on one side of the building. So we installed a stormwater reclamation system which captures all of the water that hits the roof on the building and repurposes that water, filters and treats that water, and reuses it. So within the building, we still need fresh potable water from the city for sinks and for showers, but every other bit of water used in the building is reclaimed and treated water. So although we were not able to get to net zero water for the project, we were able to reduce the potable water consumption by 88%. This is just some diagrams. If you go into the base building, the blue box that you see is a very large 11,300 gallon stormwater vault. And again, that's collecting all the water that hits the room. And then that water is transferred to the yellow box below it, a stormwater treatment room, where about 1,000 gallons a time is taken in and treated and disinfected and is used again for predominantly for flushing water, but also for the green wall and for the PV washdown. This is a picture of the actual room installed. That white tank on the back is the clean water tank, and the rest of the devices are part of the purification system. We used on the project what is called a radiant sealing system, and a lot of people talk about this as being a innovative new system, and it's really not. This is a system that has been used around the world. It's been used effectively in Germany since the 1960s. It's used extensively throughout Europe. It was tried in the 1970s in the US, but they had some early failures and the US got away from it, but now it's making a comeback, and the attributes of this system I think are really important to the desire to get to net zero energy. But it's a very simple system. Essentially, it's a metal sealing grid with the serpentine copper pipes on the back and cooler water, not chilled water, but cooler water is circulated in relatively small quantities through the piping, and it lowers the surface temperature of the ceiling. There's then a radiation exchange that happens between the humans in the building and the ceiling. So it's much, much different than the air-based systems that we've been accustomed to, where your body feels warm and cold air is blown onto your skin. This system is based on radiation. It would work even if there were no air in the space. It would work in a vacuum. as it's a radiation exchange. So very different type of cooling, but as with radiant heating systems, the thermal comfort associated with these systems is really superior. The energy profile of it is, we've modeled the systems against many others, and it always proves out to be the most high-performing system compared to other mechanical systems. So there's one image of an installed radiant sealing system. At first glance, you might not notice it as being much different. And this is a project that I worked on in China. It is a 2.2 million square foot office building in Guangzhou that is all cooled by radiant ceilings. I like to show this image because the incorrect buzz that people will often say about radiant ceilings is you can't use them in hot and humid climates because they'll condense. Well, Guangzhou, China is one of the hottest, most humid places on Earth, and they've never had a drop of condensation. So the real answer is, if properly designed, the system works anywhere in the world where you need cooling. And this is a conference room up on what they call the prow within AGU's building. And if you look at the ceiling, you'll see the slight difference between the ceiling tiles in the middle and towards the edges. And the ceiling tiles in the middle are your more conventional acoustic lay-in tiles. It's the ceiling tiles that are on the right and the left that are active radiant ceiling panels. So the cooling for the space is done by the panels. Now you will notice that there still are a couple of air diffusers, and the reason for that is we still do need to deliver air to the building, because you still need air for the ventilation system, but they are not doing the cooling for the space. The cooling is done by the ceiling plane. So photovoltaics, we need an energy source, and like I said, all net zero energy buildings need some kind of renewable energy source to be able to net out to zero, and our building is no different. AGU really adopted this 4-step generation, reduction, absorption, and reclamation strategy, and the PV is the one and only generation strategy used for the project. And again, this is a 5-story building, so we needed to get our energy use intensity very, very low to have any chance of putting enough PV on the roof to be able to get to that net zero condition. So we had to be smart about it. So the PV is a little bit different than most PV systems that you'll find, in that the PV system generates DC power. That's not unusual. What is unusual is we use that DC power throughout the building. Most buildings will take that DC power, they'll go through inverters and rectifiers, and they will change the DC power to AC power, and then use the AC power because that's what most buildings need. The problem is that there's losses, there's line losses, there's transformation losses that take place when you go from DC to AC. The reality of it is technology that we use inside buildings has changed a lot. Most people used to use desktops. Now most people use laptops. Lighting used to require AC power for the fluorescent lights. Now the LED lights work perfectly fine with DC power. So we're finding ourselves converting our AC to DC power in buildings anyways. So the thought here is, why do that? Why not produce DC power and then use DC power and eliminate all that unnecessary electric gear and eliminate all those unfortunate power losses? So to get the PV on the roof, again, first the roof needed to be scraped clean. Part of the envelope improvements, we needed better insulation up on the roof. And we also, AGU has an amenity space that was to be built on the roof. Green roof is put along the edges of the roof, and our new stormwater collection system needed to be added. So that was the roof before. This image shows the beginning of the support system to support the PV array that extends over the entire roof and even a couple feet out beyond the roof's edge. This is just an elevation showing that PV extending again over the roof and a little bit beyond. And this diagram shows sort of an earlier version of the PV layout and the final version of the PV layout. In the earlier version, essentially the entire roof was covered with photovoltaic panels. These panels are about 5 feet long by about 3.5 feet wide. Each panel generates about 360 watts of power, and we packed them in as tightly as we could. One of the comments, and then I would say on the left-hand side, we have opaque panels and we have translucent panels, but really no ability for sunlight to pass through that solid surface. When we met with Historic Preservation Review Board, there was some comments that perhaps it would look a little bit too dark up there, and there was concern about shadows being cast down on the sidewalk. So we had to come back with a second layout where we provided some spacing. We geometrically managed to do that without losing any panels, and in total we're able to get 714 PV panels on the horizontal and the vertical up on the roof's edge. So I believe it's about 330,000 megawatt hours of power generation every year. And this is a rendering of that outdoor space up on the roof, showing some of the gaps between the panels with the light passing through. And then a rendering of a eagle's eye view of flying over the building. So again, now that we have all this DC power, now we need a DC power microgrid to work within the building. This is one of the more cutting edge strategies used in the building. This image right here is known as a power hub, and this power hub has the ability to take inputs from either AC power or DC power and distribute DC power throughout the office space for both lighting and for workstations. So this is one of the engineering diagrams. Each one of those red boxes represents an above ceiling power hub distributed through the building. And again, this power hub has the ability to take AC power from the power grid during times when it's dark out or it's rainy or snowy or you don't have that sunlight. And then when the sun is out and the PV array is generating power, it can accept that DC power directly into the power hub. And then again, it distributes DC power throughout the space. So here's one of the diagrams. It's a 24-volt system. The 24-volt system works fine for the lights. When we extend that system down to the desktop, in the upper right-hand corner, we have something that is known, we call it a brick, mounts to the bottom of the desk. You know, different laptops require slightly different voltages. So this brick gives the ability to fine-tune the DC system to provide that optimal voltage for the equipment used at the desktop. And then an image of one of those DC connections. So one interesting thing to note is now with this type of system, you can be distributing power throughout an office space for both lighting and workstations, and it's all low voltage power. You don't necessarily need a licensed electrician to do all that work. Here's an image of the lower level in the building with the DC powered LED lighting in the ceiling. And now I'm going to talk about the last system in the building, and this is probably one of the most complex and generates generally the most number of questions I get when I present this project, and it's called a sewer heat exchange system. AGU is the first building in the United States to use one of these types of systems at a building scale. Since installed, there's been several others, but again, like I said before, AGU did not want to be a guinea pig. They said they did not want to put any system in that hasn't been used in the world. So we said, well, you know, does it have to be the US? Could it be a different country? And they said yes. So we found a couple of installations overseas, over in Denmark and in Switzerland. And we took AGU, representatives from HEU over there to look at the systems, talk to the building engineers, and become comfortable with the technology. And then they were okay moving forward with the system. So this is the absorption strategy that I mentioned earlier on. The notion of looking outside the building and looking for energy sources that exist that can be drawn in for the benefit of the building. When we looked around to see what we had to work with, we found treasure in our front yard. Only the treasure was not in the form of silver or gold. It was in the form of raw sewage. So about 8 feet in front of the building and about 30 feet down was a massive combined storm sanitary line that had been installed more than 100 years prior. And we said that is a source of energy. That's a source of energy that could be used for the benefit of the building. So this system dates back to the late 1880s and early 1890s. So it's pre-World War I engineering. The system prior to this, Washington, D.C. did not have a good way to remove its sewer from its buildings. So they had a major construction project to extend brand new sewer lines underneath the city in both the northeast and northwest quadrants of the city. This is a site plan showing our building, and there it is. That purple line is this line. Again, it's 30 feet down and just a few feet off of the edge of the building. And this was a treasure. When we started to study the water flowing through this, we were able to put measuring devices in the water and assess the water flow, the water temperature, the water velocity, and all the peaks and valleys that we see through a given day and through the months, and determine that there was adequate energy to do something good with that water flow. So the basic idea is that we would punch a hole in the sewer. We would extract water into an adjacent wet well. We would clean the water in that wet well as best we could, and that wet well would then become essentially a geothermal heat sink source for the mechanical systems in the building. So that was the idea. Now, you might imagine when we approached DC Water, the water utility, and said, we're going to poke holes in your 120-year-old system, that there was some hesitation on their end. But the more we talked about it, the more they understood that not only would this be a very sustainable thing to do for this building, but there's a potential business potential for DC Water, meaning that if this water is of value, then maybe it's something that could be sold to other customers. And they stopped calling it sewer water and they started calling it their asset. So this is the early stages of cutting through the top of the existing sewer line to be able to properly reinforce it so that we can then punch holes through the side of it to extract the sewer water. So on the inside of the sewer pipe, the steel reinforcement had to be added, and what's called a GEOCRETE system to then cover that steel with a layer of concrete so the steel doesn't corrode. And all of this again is put in for fear that this digging around and putting a hole through the side of it would translate into a failure in the system. It would somehow crack or collapse, and it would be very expensive to replace. So this is all for safety's sake. This diagram shows how this works. Again, if you can see my cursor, this is the 110-year-old pipe, sewer pipe. Adjacent to that, we dug a hole. We dug down even deeper than the sewer pipe. We went down about 38 feet or so, and water is extracted from that sewer pipe into this well. This machine that we call a Rock 4 system lifts up the water and drops the solids back into the pipe and continues that ongoing screening so that what we're left with is a bathtub of not clean, but not so dirty water to use for the building. So on the left-hand side is the beginning of the installation of this wet well, and on the right-hand side, lying in the garage on its side, is this Rock4 system, this device that screens and removes the solids from the building. Then when we have that water, we bring that water right inside the building and into a very special, especially designed heat exchange unit known as a Hoover heat exchanger. And this is a rendering of what it looks like. And this is the actual device showing up on the truck, ready to be installed in the building. And again, the first one of its type to be installed in the building in the United States. And then the final installed condition. So within this one enclosed room, we do have sewer water that flows into this big tank. And there's about 500 gallons that fills this tank. We extract the energy from it, and then it's flushed out and refilled, and that process repeats itself over and over again. There is a system of plastic rings that drag across pipes inside this unit once a day to remove solids. There's an auger at the bottom that takes the last bit of solids out of the building. And there's even an air compressor that agitates the water, adds bubbles to enhance the heat transfer effect. If you walk into this room, some people can sense a slight sewer odor, but that is only within this one mechanical room. It is not detected anywhere else in the building. Because of this system, we do have a very small chiller, a heat recovery chiller that provides all the hot water and chilled water for the entire building. It's a very small unit, and it only needs to operate during times that we can't get free cooling. That's in the very hottest months and the very coldest months. But for most of the year, the heating and cooling for the building comes from this very small, 5 foot tall, 2 foot wide heat exchanger that is really exchanging the energy from that dirtier water to the cleaner water, which is then recirculated through all the radiant ceiling panels throughout the building. There's a lot more, and anybody who is interested in this technology, and there's a lot of detail to it, too much to get into today. But as it turns out, our second session of this webinar program is 2 weeks from today at noontime. And one of our best mechanical engineers, Joe Diano, will be spending an entire hour talking specifically about heating and cooling using city sewer water. So if you're interested, mark your calendar. So the results of it, as you can see, with every single pane of glass being an independent IP address and data point, there are more data points in this building than any project that I've ever been involved with, and AGU is big on data, and the scientific community and all of their members are also quite interested in data. So all the data is collected. The building engineer has access to all of it. A large subset of it is made available or will be made available on AGU's website through its membership portal. There is some data that will be free and available, very transparent, open access to everybody through their website. And then when you go into the building and take the tour, there are these beautiful digital displays that you can touch screen. You can look at every system in the building and see how it's functioning at that moment, on that day, that week, that month, etc. So where we started out, the blue represents the amount of electricity that was consumed per year in the building, and the red, the amount of natural gas, all in terms of kilowatt hours. And through all the various measures, we were able to reduce that number. And in terms of EUI, we were able to go from an EUI of about 85 down to an EUI of about 11. 11, for those people that are in the field of high-performing buildings, that is a very low number to hit. And then we added the PV array, which is responsible for the equivalent of about 13 EUI. So the light orange there is what the building consumed before, 1,500 megawatt hours. Through all of the reduction, absorption, and reclamation strategies, that was reduced to about 300 megawatt hours. The PV array has the ability to produce 346 megawatt hours per year. So the modeled performance of the building when it's been up and running for a year should net out to 46 megawatt hours a year, plus or minus, depending upon weather and a whole host of other factors. But it is designed to be a positive energy building. In terms of making an impact, AGU's their position is that just having their building perform very well is not enough. It only makes sense to go through this effort if you can communicate the results and the opportunities and the strategies and the performance and the outcome with others. So a lot of work has been put into how this building and its approach can be communicated to the local community and to the members. This is a before and after image of the building with the new prow and the solar array on the roof. You'll notice a big difference along the streetway. It was very much an inward-looking building before, and now it's been designed to attract and draw people and the community into the building so that they can learn about AGU as an organization and learn about the buildings and all the strategies within the building. Tours are given sometimes multiple times a day within the building. So if you're interested, you can contact AGU and arrange for a tour. As you take the tour, it'll take you by all of the interesting bits and pieces, including all the major mechanical rooms. First time in my life, the client has had an interest to put all our mechanical rooms behind glass. But not only are they very visible, but very well suited with signage so you can see what all the elements are doing and how they're contributing. And then up on the prow, and I like this image for a couple of reasons. One is that a lot of people, when they think about or hear about sustainable buildings, high performing buildings, net zero energy buildings, they think about all the compromises that they're going to have to make, and they imagine almost a treehouse type condition. And I think what we're shown in this building is that you can have a very high-end, Class A, modern office building in an urban environment downtown that does not look like a treehouse. It looks exactly like you would expect a Class A office building to look at, but it is operating at net zero. But the details are interesting, and even looking at this conference room table, this conference room table was made when we renovated the building. We had to replace all the toilet fixtures in the building to come up with put in low flow fixtures. All the existing fixtures were crushed into a terrazzo type material and used on flooring throughout the building. And for this conference room table, which is essentially made of the crushed glass from the exterior of the building and the crushed toilets that were taken out. So it's sustainable, not just from an energy and water standpoint, but very much from a material standpoint as well. The building is already making a difference. Last year, when Mayor Bowser signed the Historic Clean Energy DC Omnibus Act, they chose the lobby of AGU as the perfect location to sign this bill into law. AGU is also the inaugural recipient of the very first Washington, D.C. Clean Energy DC Award given last year from the Department of Energy and the Environment. And again, it's a building we're very proud of, and a building that we believe is doing exactly what it was intended to do. Not only operate in a very high performing way, but also to tell a story and to hopefully inspire other owners, architects, engineers, developers to do better than this, to take what was done here and take an extra 1 or 2 steps. So that's the presentation, and I'm new at this GoToWebinar, so I'm going to see here if I have the ability to scroll through any questions from the group. All right, I see one question that was put up that says, will this presentation be archived online afterwards? And it has been recorded, and I believe that it is our intention to put this presentation in a location that that can be accessed through our through the interface engineering website. All right, sorry, going through here. What software did you use for energy modeling? The software that was used is a program by the name of Energy Plus, and Energy Plus relies on DO2 computation engine, but Energy Plus was the program used for modeling. Can this presentation be available to us? Yes, again, what we'll do is once we've placed it in a place that can be downloaded, we will send an email out to all of those that are in attendance today, and you can download it at your leisure. Next question is, what is the CO2 measurement of the 100% recirculated air for the HVAC? I don't have that exact value. Again, I think I'll have to respond to that in writing, but all I can say is that CO2 is the major element that is being measured through the return, but it's not the only one. There are 16 altogether, and we have to demonstrate that the parts per million of all 16 are in lesser concentration than the outside air before the system will then reroute and take the outside air from inside rather than from outside. But the exact measurement of CO2, I don't have an answer for that. Next question, what is the U value for the glass that had been used on the project? You guys are asking me really tough questions. What I promise I will do is I will be able to download all these questions, and I will, along with posting the presentation itself, I will also post a document which are the questions and our answers to all the questions posted as best as we can answer them. It might take me a couple of days to get that document put together, but I will get answers to that. Next question is, what can be the % of savings with radiant sealing systems? I will say here that when we compare and contrast, we often use a VAV system as a baseline system to compare against in Washington, D.C. And there are other systems such as DOA-SPOC systems or systems such as chilled beam systems that can reduce, by 10, 15, 20%, but we've been able to see savings up to 35% on the energy model by using a radiant sealing system. The AGU building is not the first building in Washington, D.C. to use this system at this scale. It's the second. The first is a new law library at American University, and I know they do give tours of that building as well. So if you're interested in seeing them, you can certainly tour AGU, but you could also make arrangements to tour the American University building, and certainly would encourage you to ask them all the questions of how they feel about the system and the operation and the maintenance. I generally hear pretty good stories. The DOS is a ventilating, radiating ceilings are tempering, but how is dehumidification performed? That's a great question. And essentially, there is a DOS unit up on the roof that is treating the outside air, and we are decoupling the DOS unit from the radiant sealing system. So essentially, the DOS unit is responsible for the bringing in the outside air or taking the outside air from the green wall, and to doing the dehumidification and reheat of that air. So the air that is going into the building is of good quality. It is also dry, and it keeps the building under a positive pressure. So the radiant system is very good at what they call sensible loads, but the latent loads associated with the outside air are taken care of by the DOS unit up on the roof. And I'm scrolling through here. There are probably another 50 questions, but I think we're out of time on the GoToMeeting. So again, we will do our best to print out all the questions and to put responses next to each and post them. And we will send an email along with the instructions to download a PDF of the presentation itself and of the Q&A. But I'd like to thank you all for taking time out of your busy day. I really appreciate it. And have a great day. Take care.